Hey folks, welcome to Chapter 2, Lesson 1, Conjectures and Counterexamples. We're going to start off with this slide, which is not in your textbook, and describes number systems. So there are many different number systems. One you're most familiar with are probably natural numbers, like 1, 2, 3, 4, 5, ad infinitum. And we use this symbol right here, this n with the double slash, to indicate natural numbers. Some people include zero in here, many do not. But think of them as counting numbers. A larger set of numbers would be the integers. Now we allow for negative counting numbers, right? If you just negate the counting numbers, all these together will be the integers. So like think the set ... -3, -2, -1, 0, 1, 2, 3, ... Those are integers. Larger than that set are called rational numbers. Now, rational numbers has this symbol Q with a slash, whereas integers had the Z with the double slash. The rational numbers are any number that can be written as the quotient of two integers. So look at this, 1/2. A quotient is the answer to a division problem. 1/2 is 1 divided by 2. That's what it means, right? So 1's an integer, 2's an integer. Since 1/2 is a quotient of two integers, it's a rational number. Likewise, here's -2/3. Well, -2 and 3 are both integers, so quotient of integers. 2.25 is also a quotient of integers. 9/4, isn't it? Let's see, 8/4 would be 2, 9/4 would be 2.25. So if I can express this decimal as a quotient of two integers, we're talking about a rational number, which is the set Q. Now there is a much larger set called all the real numbers, and that's going to include all the irrational numbers like square roots of 2, square roots of 3, square roots of 5, so on and so forth, and all of the numbers that are irrational and transcendental. There are only a few of them, actually. Pi and E, these are really special numbers that God baked into the universe, and they're pretty incredible. In fact, I challenge you to get on Google when you have some free time and say, what is pi? What is E? And look for some deep answers. Maybe you'll find some on YouTube. More just the superficial answers, right? All right. These were the numbers pi and E, 3.14159, so on and so forth. It's transcendental. This number will continue on forever. It's got an infinitely long list, and there's no repeating decimal places. E is also transcendental, 2.718, blah, 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 blah. And you should be familiar with these numbers. Hey, when you think of pi, you probably think, oh, I have seen pi in this equation for a circle, right? The circumference of a circle is equal to pi times diameter. So I guess if I just divide by d, I get pi is equal to circumference divided by diameter. And so many people say, hey, that's the definition of pi. I don't know if that's the definition of pi, but it is true about pi, and it's probably the most well-known kind of definition of pi. Pi is something else. It's a constant that God has baked into this universe that pops up everywhere. I'd love to give you an example of some of the crazy places pi will pop up. That has nothing to do with circumference divided by diameter, or at least nothing overtly about circumference divided by diameter. Now I'm going to play a video here. I don't know if it's going to record in this type of slideshow. So I've added a link down here that you could copy, or if you want to make it easier, just go to YouTube, type in the search bar for YouTube, I'm still astounded this is true, 3B1B stands for 3 blue 1 brown. He's a mathematician. And just watch the video. It's like 30 seconds. And you're like, what? Okay. So I'm going to try playing the video and we'll see if it works in here. If not, you can certainly do that yourself. All right. No, I'm sorry, it did not. So hopefully you went and watched the video. If not, pause and go back and watch it. Okay, we're into the textbook now. Everything you see from here on out will be from the textbook. Inductive reasoning is reasoning that uses a number of specific examples to arrive at a conclusion. When you assume that an observed pattern will continue, you're applying inductive reasoning. A concluding statement reached using inductive reasoning is called a conjecture. So today we'll be doing inductive reasoning. In inductive reasoning, you're given a number of examples and you make a conjecture about those examples. That's what inductive reasoning is. Write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. All right, so we're given some movie show times: 8:30 a.m., 9:45 a.m., 11 a.m., 12:15 p.m. Based on those show times, can you guess when the next show time would be? Hmm, you probably said, well, an hour and 15 minutes later, it should be 1:30 p.m. Let's see. If I look for a pattern, yeah, it looks like I'm adding an hour and 15 minutes between each show time. So now I make a conjecture based on the pattern. The show time is 1 hour and 15 minutes greater than the previous show time. So the next show time would be 1:30 p.m. Notice the conjecture has two parts. It's a conjecture about the pattern you see, and then a conjecture about what the next show time will be. All right, here's another example. Looks like we have squares here, and this has 4 segments. This has more than 4 segments. It has 10 segments, 18 segments, 28 segments, 40 segments. But you can see what's happening. You're adding a square, a larger square each time. So how do we go from 4 to 10 here? We're short of counting. Well, there's 4 sides on this square. Okay, this square would have 2, 2, 2, 2, or 8 sides. 8 segments, but then again, these two are shared. So 8 minus 2 is 6, so 4 plus 6 is 10. Likewise here, I'd be adding 3 plus 3 plus 3 plus 3, or 3 times 4, which is 12. But this right here contains 2 by 2, or 4. So take 12 off 4, you get 8. 10 plus 8 is 18. So you see how these numbers are working. All right, what's the first thing we're going to do? We're going to look for a pattern. Just lay out the numbers and then see what the pattern is. Plus 6, plus 8, plus 10, plus 12, and now make a conjecture. My conjecture would be the next figure will increase by 14 segments. So the next figure should have 54 segments. Notice the conjecture includes both my knowledge about the pattern and also my prediction from the pattern. That's my conjecture. How do I check to see if my conjecture makes sense? Well, I could draw the next picture, couldn't I? I could draw the next figure and check your conjecture. So if you draw the next figure, you count it out, it's 54, which is exactly what we'd expect it to be. All right, guided practice. Write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. I'm going to urge you that for these next few problems, that you pause the video, try them yourself, and then come back. This particular set of doctor follow-up visits happen in December, May, October, and March. So what are you supposed to do? You're supposed to look for a pattern, try to discover the pattern, and then make your conjecture. Go ahead and pause it now, and then come back. All right. So what pattern do we have here? Well, it looks like every 5 months. I think you might have been thinking, I thought it was every 6 months. Well, we don't include the first month because that's like time 0. And the next month, January, would be time 1, and then February time 2. We'll start from time 0, not time 1. Makes more sense. So 5 months at a piece means that my conjecture is a follow-up visit occurs 5 months after the previous follow-up visit. So the next visit will be in August. August will be my next visit. All right. How about this one? Remember what the 2 steps are here? Look for a pattern, make a conjecture. Go ahead and try it. Pause the video. Come back when you're ready. All right. Well, it looks like we're subtracting 6 each time. So my conjecture is the next number is 6 less than the previous number. So the next number should be negative 14. One more. Well, this is geometric in nature. What are the 2 steps again? Look for a pattern, make a conjecture. Go ahead and pause it and come back. All right. You might have looked for a multiplicity of patterns here. Only from experience would I intuitively know that they're asking me to look for the pattern of the blue triangles. You might have found other patterns, but the blue triangles are the pattern they're looking for here. Notice what you go from the first triangle to the second triangle. What you do is you insert this white triangle into the dark triangle. Likewise, you have a dark triangle up here, you're going to insert a white triangle. You have a dark triangle down here, you're going to insert a white triangle. You have a dark triangle down here, you're going to insert a white triangle. That's how this thing works. But what you notice then is there's a regular pattern in the dark triangles. You go from 1 to 3 to 3, 6, 9. So what's the pattern? Looks like you're multiplying by 3, right? Dark triangles, 1, 3, 9. Yeah, it looks like you're multiplying by 3. So what will be your conjecture? The number of dark triangles in the next figure will increase by a factor of 3. Whenever we multiply by 3, we say we increase by a factor of 3. You might want to say that language out loud to yourself. So the next figure will have 27 dark triangles. How can we check this? Well, just draw the next triangle. Remember, each one of these patterns has 3. There's one of those up here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of those 3s will be 27. So perfect. All right, second type of problem is this. A little more involved, not much. Write a conjecture about each value or geometric relationship. List or draw some examples that support your conjecture. The sum of 2 odd numbers. All right, what steps will you need? First, you're going to have to actually list examples. All right, well, the sum of 2 odd numbers. That means take 2 odd numbers and add them together. Well, 1 plus 3 is 4. Plus 5 is 6, 3 plus 5 is 8, and 7 plus 9 is 16. Notice 1 and 3 are odd numbers. 1 and 5 are odd numbers. When I take their sum, what do I notice about all the sums there? See a pattern? Yeah, all the sums are even numbers. The sums 4, 6, 18, and 16 are all even numbers. Now I make a conjecture. What's my conjecture? The sum of 2 odd numbers is an even number. Now let's stop and think about inductive reasoning. Am I sure that the sum of 2 odd numbers is an even number? No, I'm not sure. I've made examples and they seem all to be true, so I make a reasonable conjecture. This is what inductive reasoning is. When you make a reasonable conjecture based on as many examples as you have. But if I were to use inductive reasoning to determine if it's absolutely true that the sum of 2 odd numbers is an even number, I'd have to consider every combination of odd numbers, the sum of every combination of odd numbers, and there's an infinite number of those combinations. So induction gets me the truth, most likely, but I could be wrong, okay? Not infallible. Segments joining opposite vertices of a rectangle. Okay, can we even envision what that's saying? What would be some examples? Segments joining opposite vertices of rectangles. So what should you draw as your examples? Rectangles, and you should do what? Create segments from opposite vertices. Here's 4 examples that I created, or I borrowed from the book. Now, next, look for a pattern. Well, there's many patterns here, right? Immediately you're going to notice all rectangles have 4 sides. You're going to also have the congruent angles. Right, but what has to do with segments joining opposite vertices? Those pink segments we just created. What do you notice about them? You might think, oh, they create vertical angles. That's true. But what's true about each of them also, and what they're going after here, is that those 2 segments are always congruent. The segments joining opposite vertices of each rectangle appear to have the same measure. Right? Now, how can you check yourself? Well, you could use a compass to confirm that. You probably already have that intuition since what we've been doing. Or you could use a ruler to check yourself. What's my conjecture then? Using the language from the top, the segments joining opposite vertices of a rectangle are congruent. Have I proven it? No, but am I pretty sure this is a reasonable conjecture based on my examples? Yes, I am. All right, these are guided practice, so you're going to want to attempt these on your own. Pause the video, come on back when you're ready. The sum of 2 even numbers. Remember, in these problems, there are 3 steps. List the examples, look for a pattern, make a conjecture. All right, pause it, come on back. All right, so if I add together a bunch of sets of even numbers, I notice that all my results are even numbers. That's my pattern. 4, 6, 10, and 16 are all even. My conjecture, the sum of 2 even numbers is an even number. Good. Let's try another one. The relationship between AB and EF, if AB equals CD and CD equals EF. Remember, you're going to list examples, look for a pattern, and make a conjecture. Let me say before you get started on this one, you're probably going to have an algebraic instinct to say this is true. You're in geometry class, and I always want you to consider geometry in all the work you do through calculus, minimum. So let's do some geometry here. Let's treat AB as a line segment, and AB being the measure of that line segment, and EF is the line segment. All right, do some geometry here, some geometric examples. Okay, pause and come back. All right, here are some examples. Notice I could use a compass to make CD from AB, and I can use a compass to make CD from EF. And then if I check with the compass, I'll see that AB is equivalent in measure to EF, congruent. And no matter how many times I try this, it's always going to work out. And so my pattern is, in each case, AB equals EF when I measure them with a compass or with a ruler. My conjecture, if AB equals CD and CD equals EF, then AB equals EF. Notice my conclusion is algebraic in nature, but my work was geometric. All right, let's try another one. The sum of the squares of two consecutive natural numbers. What? We're supposed to list examples, look for a pattern, and make a conjecture. The hardest part about this problem is, can you even conceive of what's being said? A sum is a what? An answer to an addition problem. So you're doing addition of the squares. What's a square? When you take the square of something, like the square of 9 is what? 81. So the square of 9 is 9 squared. The square of 4 is 4 squared. Of two consecutive natural numbers. Well, what are natural numbers? Those are the counting numbers, like 1, 2, 3, 4, 5. What does it mean to say they're consecutive? We choose 1 as the first number, then 2 is your second, 5, and 6. All right, so I want to add together squares of two consecutive natural numbers. All right, give it a shot. All right, we're back. Well, 1 squared plus 2 squared equals 5. 2 squared plus 3 squared equals 13, 25, 41. Notice I'm taking sums. Notice that 1 and 2 are consecutive natural numbers. 2 and 3 are consecutive natural numbers. I'm squaring them before I add them. So what do I notice about the pattern? Well, there's quite a few patterns here, but one of the obvious patterns is 5, 13, 25, and 41 are all odd numbers. Therefore, my conjecture, the sum of the squares of two consecutive natural numbers is an odd number. Notice my language here. I'm taking my language right from the original question. The sum of the squares of two consecutive natural numbers. Look at my conjecture. The sum of the squares of two consecutive natural numbers is an odd number. Noun, verb, noun. That's how we always talk in math. All right. Last thing in this chapter is counterexamples. So to show that a conjecture is true for all cases, you must prove it. It only takes one false example to show that a conjecture is not true. This false example is called a counterexample, and it could be a number, a drawing, or a statement. All right. You're clearly watching this. Maybe there's other people in the room with you. Maybe they're not. Maybe there's people on a video in the background. God knows what's going on right now. But let's say you were in a room of people. Okay, and I was there in the room as well. And this statement was made. All men have hair on their heads. Okay. Point to one counterexample that proves that to be false. Yeah, that guy, me. Right? I prove it false. You only need one counterexample to prove that a truth claim is false, if indeed it is false. All right. Find a counterexample to show that each conjecture is false. If n is a real number, then n squared is greater than n. Remember, real numbers is kind of the broadest category of numbers that we're considering so far. It's all numbers that don't include imaginaries, if you've ever heard of those. Okay. Can you think of a counterexample? Well, how about the number 1? If n equals 1, then 1 squared is not greater than 1. Right? 1 is equal to 1. That's a counterexample. If you choose any number n that's greater than 1, of course this is true. Right? If I choose the number 3, 3 squared is clearly bigger than 3. But if I choose 1, wow, 1 equals 1, so 1 squared can't be greater than 1. One counterexample to disprove. How about this one? If JK equals KL, then K is the midpoint of the line segment JL. Okay, just picture this with me. Just quickly picture it in your head. let's say this is our line segment. Okay, where would the midpoint be approximately? If this is segment JL, then K would be right about where my finger is, right? Right about where my finger is, right about there. Well, it certainly seems that this segment right here is congruent to this segment right here. In fact, the midpoint would definitely bisect this line segment. So why in the world would this ever be false? Is there any counterexample you can come up with? Yes, there is. You're thinking purely in what? Is this R1 or R2? R1, right? It's just a line. But what if I allow myself to be an R2 on a plane? Well, then we get this kind of scenario. Look at it now with me, would you? Here's J, here's K. So JK is congruent to KL. You can see that by these tick marks. JK is congruent to KL. But clearly JL, if I want to find its midpoint is right here, or the pointer is. Is K at that point, at that midpoint? No, it's not. So as long as you allow yourself to be an R2, you can easily come up with a counterexample. Interesting, right? Sometimes you consider R1, sometimes R2, sometimes R3. This is how the book puts it. When J, K, and L are collinear, meaning on the same line, the statement's going to be true, like I showed you with this pen, right? But when J, K, and L are non-collinear, not on the same line, i.e. they're in R2, then the conjecture is false. As you can see right here, JK is congruent to KL, but K is not the midpoint of JL. This is the midpoint of JL. All right, now you try. Pause and come back. Remember the steps. Oh, sorry. I can't go. I'm sorry. I can't go back now, unfortunately, in this mode. So let's just talk this through. If n is a real number, then negative n is a negative number. Can you think of a counterexample? Well, sure. N equals any negative number, like -4. If you plug in -4 for n, you get -4, which is 4, and that clearly is not a negative number. All right. You try this one. Promise I won't click any buttons. If angle ABC is congruent to angle DBE, then angle ABC and DBE are vertical angles. Is that true? Not true? I mean, vertical angles are always congruent. But can you come up with a counterexample where you have congruent angles that are not vertical? Give it a shot. Come on back. All right, we're back. Yeah, look right here. Angle EBD is congruent to angle ABC. Can you see that? They have little congruency markers here. Are these vertical angles? No. The only way to create vertical angles is to have two intersecting lines. Then the opposite angles there are vertical angles. There's two pairs of them, right? But that's not the case in our picture here, right? That's not a straight line. That's not a straight line. And yet this angle and this angle are congruent. So they're congruent, but not vertical. You come up with a counterexample. Now let's see how the book says it. When points A, B, D are non-collinear, not a straight line, and points E, B, and C are not collinear or not on a straight line, then the conjecture is false, right? Because you don't have vertical angles here, but you do have congruent angles. All right. Now you just want to think through these questions before you go on to your homework. What's inductive reasoning? If you're unsure, you can look in your textbook, you can look in the slideshow, the class notes, or in the notes you might have just taken. What's a conjecture? Look in the same places. What are 2 steps when writing a conjecture describing a pattern in a sequence? What are the 3 steps when writing a conjecture about a value or geometric relationship? And finally, what is a counterexample and what is it used for? All right, so you want to make sure you're familiar with this language, that you kind of define this language. All right, so if you have to look it back up, look it back up, but answer these questions and make sure you're doing them well.